Nitrogen is in group 5A of the periodic table, so it has 5 valence electrons. We can draw the Lewis dot structure as 1, 2, 3, 4, 5, and what you'll notice here is that nitrogen, when it's neutral, can form 3 bonds with those unpaired electrons, and it would have that one lone pair at the top. That one lone pair ends up being crucial for the behavior of nitrogen-containing compounds, because the lone pair can be exposed to the outside world, and so can knock into things like hydrogens that are slightly positive and rip them off. This lone pair can act as a base. Indeed, the poster child of a Bronsted-Lowry base, so that's a base that accepts protons, when you first were introduced to it in general chemistry, would have been ammonia. Ammonia is the nitrogen version of water. So nitrogen just surrounded by hydrogens. Water is oxygen just surrounded by hydrogens. So it's sort of the smallest nitrogen, the smallest stable nitrogen compound. That's ammonia. And you can almost see in the name ammonia the title of this chapter. You can take ammonia and replace the hydrogen with some carbon chain. You could do that for 1 or 2. You could do it for all 3. But if you replace the hydrogen in ammonia with a carbon chain, then what you end up with is an amine. Amines are derivatives of ammonia. But notice that when you change ammonia into amines, all you're changing are the hydrogens. Crucially, what you don't change is the lone pair. That lone pair still exists there, and it's still able to act as a Bronsted-Lowry base. It still has a negative charge that's exposed to the outside world, and so it's able to accept H pluses. Now, how good of a base an amine is, and this basicity of amines determines a huge amount of their behavior. It's incredibly significant. There are a whole class of neurotransmitters called monoamines that are defined by their amine functional group, and it's the lone pair of the amine that can act as a base that largely determines the behavior of the neurotransmitters. And alkaloid drugs, things like cocaine or morphine or caffeine or novocaine, it's the lone pairs on the nitrogens in those amines that give those biologically active molecules the behavior that they have. Other examples are Nexium or Viagra. All of those are amine molecules, and their behavior is largely explained by, at least their reactivity is largely explained by the lone pair on the nitrogen acting as a base. So when they give us 2 molecules here, and they're trying to train us to see that lone pair, and whether it is a strong base or not, we want to first take the molecules that they give us and draw in the lone pair. So we'll take these, we'll make them a little bit bigger. Now we know nitrogen, if it doesn't have a charge, has 3 bonds, and crucially, that one lone pair. So I'm going to draw the lone pair in here on each of these nitrogens. And what we want to think about is which of those lone pairs is less stable, because the less stable one will rip H pluses off of other molecules more often and will act as a stronger base. So which is more unstable, which is less stable? A really important principle for stability is that if something is localized, if you force a charge to be in a small space, then it's unstable, because the charge repels itself. The charge in one place repels the charge right next to it, and it wants to get apart. So if it's localized, then it's unstable. If it's delocalized, so spread out over more than one atom, then it becomes more stable. It dilutes the charge. Now, there are a few ways that we've learned to spread charge out, but one of the most important and one of the most efficient is resonance. And there were 5 resonance structures that you would have learned in Organic Chemistry 1. And if you are unfamiliar with those, let me know. I have hours of videos that go over practice, that introduce and practice those 5 patterns. So let me know, and I can send you those to help master recognizing localized and delocalized electrons. In the case of amines, one pattern is going to be especially important. One of the 5 patterns is when you have an allylic lone pair. An allylic lone pair is a lone pair that's one atom away from an atom in a double bond. So on the atom right next door, you have an atom in a double bond. What's significant about that is that when you have a double bond, you have a pi bond. And a pi bond has 2 parallel p orbitals. It's the overlap of those 2 orbitals, those parallel p orbitals, that creates the second, or pi, bond here that we symbolize with a little stick figure line. And so you have these 2 parallel p orbitals. If you have a lone pair on an atom next door to that, the lone pair can start flying around in a p orbital and then spread itself out over all of those parallel p orbitals. And it becomes more stable, less reactive. So you can see that because this lone pair here on the molecule on the right, this lone pair is allylic, it's one atom away from an atom in a double bond, the lone pair is able to fly in a p orbital and spread itself out over 3 atoms. That delocalizes the lone pair, dilutes the instability of it in space, and makes it a weaker base. That's a weaker base because the lone pair, which is what would accept the H+, is not very unstable. It's stable, so it doesn't have a lot of motivation to steal an H+. On the other hand, this lone pair here is not near any p orbitals. It's just stuck in space. It would exist in an sp3 orbital, pointing out in space, feeling the repulsion of these bonds. And it's localized. It's stuck on that one nitrogen atom. And so because it's localized in that one place, it is unstable. It's looking for a way to stabilize its negative charge. It bumps into an H+ on another molecule, accepts the H+. It is the stronger base because it's not being spread out or delocalized through resonance. So let's take this sort of principle, this guiding principle, and explore it with a couple more molecules. So we know that if it's localized, it's going to be unstable. If it's delocalized, it will be relatively stable. So we can take the molecules they give us here, and we'll make them a little bigger so it'll be easier to talk about them, draw things in. Okay, so in these molecules, the first thing you want to do is to draw in the lone pair, and from now on, anytime you see a nitrogen, see the lone pair. It's almost never drawn in. But because it determines the behavior of the nitrogen so much, you always want to be able to see it on the nitrogen. Now, the nitrogen will only have a lone pair if it has just 3 bonds. If it has 4 bonds, then the lone pair is making that 4th bond, so then it wouldn't have a lone pair. So you have the lone pair when the nitrogen has just 3 bonds. Now let's think about this. In both of these cases, you might say, well, this on the left, the lone pair there is allylic. If you have, it's one atom away from an atom in a double bond. You have p orbitals here that are parallel to create the pi bond. You have p orbitals next door that are parallel to create the other pi bond. And why can't this exist in a p orbital and spread out over that whole molecule? 5 different atoms, spread out in space, very delocalized, very stable. But what you'll notice here is that you have a situation where you have to consider aromaticity. After all, you could go through that same analysis for this molecule on the right and think the same thing. Parallel p orbitals all the way around here. This could theoretically fly around all of those, but you have to see, if you have parallel p orbitals going around the whole length of a ring, you have to see whether you have a Huckel's number, if you remember a Huckel's number, of pi electrons. The Huckel's number was 4n plus 2, and that was just summarizing a pattern. So if n is 0, then it's 2. If n is 1, then this is 6. If n is 2, then it's 10, and so on. If you have these numbers of pi electrons in the ring, then it's aromatic. If, on the other hand, you have parallel p orbitals around the whole molecule, but you don't have this number of pi electrons, then it's anti-aromatic. Aromatic, we said, was very stable. That's what aromatic means. It's a ring that's very stable. And an anti-aromatic ring would be very unstable, very reactive. Okay, so here, if we imagine this scenario on the left, if we had these p orbitals here, and we imagine this in a p orbital too, all the electrons in p orbitals would be 2, 4, 6. We would have 6 electrons in p orbitals. Those would be called pi electrons. And that is a Huckel's number. So this is aromatic, and so very stable. Okay, now let's think about this one on the right. Let's say we know we have p orbitals on these carbons to create those pi bonds, the second bond that you have there, and then this lone pair on this nitrogen could exist in a p orbital. How many electrons would we have there? Well, we'd have 2, 4, 6, 8. If the lone pair existed in a p orbital, that would have 8 electrons. That is not a Huckel's number, so it would be anti-aromatic, which would be very unstable. And in fact, the molecule twists and turns and bends so that this does not happen, because this is such an unstable scenario. What it does is it prevents instead of the lone pair existing in a p orbital, instead it exists in an sp3 orbital pointed out in another direction that doesn't overlap with the rest of these, so that you don't meet the first criterion of aromaticity, which is having parallel p orbitals on every atom all the way around a ring. If you don't have that, so if the molecule bends a little bit, rehybridizes, if the electrons fly in a different way, in the shape of an sp3 orbital pointing in a different direction, in that case, this is non-aromatic. To be anti-aromatic, you have to have parallel p orbitals on every atom around a ring. By making the electrons fly in a different direction, in a different orbital, that you destroy them. You don't have parallel p orbitals all the way around in a ring. But just to finish that thought, to have an anti-aromatic compound, you have to have parallel p orbitals all the way around a ring, and the number of electrons in the pi bonds cannot be a Huckel's number. So here what happens is the electrons on the nitrogen fly in a different way. They end up being in an sp3 orbital, and so this is non-aromatic. So that the molecule doesn't just immediately break down. Anti-aromatic molecules very rarely last very long. And so this molecule stabilizes itself by becoming non-aromatic. Nonetheless, if we compare this molecule on the right with the molecule on the left, we can see, and let's sort of get rid of the extra details here so that we can see what's essential. We can see, actually, that in this molecule on the left, the aromatic molecule, it's very stable. These electrons are spread out over 5 atoms, so they're very unlikely they have very little motivation to react with or steal a slightly positive hydrogen somewhere else. And so this molecule on the left will end up being a weak base. On the other hand, while it's not anti-aromatic, this nitrogen here with the lone pair in the sp3 orbital, that lone pair is stuck on just the nitrogen. It is localized on the nitrogen. And so it would love to spread its negative charge out a little bit more, maybe by forming a bond to another nucleus. And so that would be much more likely to rip a slightly positive hydrogen off of another molecule. In other words, this is much more likely to act as a base. So this is a stronger base. So of these two molecules, this lone pair would be more likely to steal an H plus from another molecule than the other lone pair. Okay, we're going to take the same principle, localized is unstable, delocalized is stable. We'll apply it to C. And we'll take these same molecules, like we've been doing. We'll take them, and we're going to make them a little bigger. Okay. Now, anytime you see an amine from now on, you want to see the lone pairs. They're almost never drawn in, but you want to see them because they largely determine how the amine is going to react in different environments. Then, to assess how reactive that lone pair is going to be, and one way of doing that is to assess what type of a base it will be, how likely it will be to steal an H+, think about how localized or delocalized the lone pair is. You'll see that this lone pair on the right is allylic to this pi bond. It's one atom away from an atom in a double bond. And so you have these two parallel p orbitals between these atoms that are creating the second bond, or the pi bond there. The lone pair can exist in a p orbital, and so it can spread out, all these p orbitals are parallel, it can spread out over those three atoms. That means it's delocalized, and so stable. On the other hand, the lone pair in this nitrogen is not allylic to any pi bonds. So it's just going to exist in an sp3 orbital that's localized or stuck on just the nitrogen atom. So that is localized. It's stuck in just one location or place, and so it's relatively unstable. It will react with stuff. And because this is more likely to react with stuff, it's more likely to steal an H+, and so this is from another molecule, and so this is a stronger base. Because the other lone pair is spread out and more delocalized, because its charge is diluted in space, the charge isn't being repelled by itself so much, it's not as likely to try to seek an escape in a slightly positive atom on another molecule. And so it is less likely to steal an H+ from another molecule, and so it is a weaker base. Okay, last one, D. Now in this one, we're going to take our same principle as before, and actually here, we'll take our same principle as before. If it's localized, then it's unstable. If it's delocalized, then it's stable. And we'll apply it to these two molecules. Now, I'm going to make these bigger so that we can draw on them a little better, see what's happening in them a little bit better. Okay, now if you look at these, okay, so you see nitrogens with all single bonds. Well, you see nitrogens without any carbonyls next to them, so we have an amine. And so anytime you see a nitrogen, you want to see the lone pair on the nitrogen. So long as the nitrogen has just 3 bonds, it also has a lone pair. And that lone pair, which is unfortunately often not drawn in, is responsible for a lot of the behavior of these amines. Now, both of these amines are allylic. They're one atom away from an atom in a double bond. And you have these conjugated systems. We're alternating single and double bonds. And those are significant because if you draw the p orbitals on all of these atoms, you see that there are parallel p orbitals on every atom in the ring. That happens anytime you have conjugated bonds, double, single, double, single. So, theoretically, this lone pair on this nitrogen could exist in another p orbital and spread itself out over all of these atoms. And if you look at the molecule next door, it might seem like that could happen too. All of these atoms have pi bonds, so they have these parallel p orbitals on them. The p orbitals go all the way around the ring. And theoretically, this could exist, well, first this is in a pi bond. And so you might wonder, can this lone pair exist in another p orbital that could spread out that way? Well, let's consider these one at a time. First, the nitrogen on the left has all single bonds in it. So it can allow its lone pair to fly in a p orbital. And here, because it's going vertical, I'm going to call it the py orbital. The x-axis goes horizontally, the y-axis goes vertically. So because these are vertical, I'll call them vertical p orbitals, I'll call them py orbitals. Excuse me. And so this lone pair can fly in a py orbital that's parallel to all of these others and maybe spread out over all of those atoms. Now you'll notice that you have conjugated pi bonds in a ring. You have parallel p orbitals on every atom in these rings, and so you have to consider aromaticity. How many electrons do we have in these pi bonds? Is it a Huckel's number? Well, we have 2, 4, 6, 8, and if the nitrogen is flying in a py orbital, then 10. 10 is a Huckel's number, and so this molecule would be aromatic. That means that it's extremely delocalized and extremely stable. And because it's extremely stable, this nitrogen is less likely to react with something. It's less likely to accept an H+ from another molecule, and so it would be a weaker base. Now let's analyze the other molecule in a similar way. First of all, if you think about the number of pi electrons, and you counted those up, you'd have 2, 4, 6, 8, 10, and if the lone pair was included, you'd have 12. 12 is not a Huckel's number. If you continue this, and so if n is 3, right, because if n is 2, it gives you 10. If n is 3, then it would give you 14. Notice that 12 is not there. 12 is what we had here. So 2, 4, 6, 8, 10, and if the lone pair is there, 12, 12 is not in this Huckel's number, so that would be anti-aromatic, which would be very unstable. And in fact, that is such an unstable scenario. This couldn't form anyway. If you notice, if you look at the nitrogen is already using its py orbital to participate in this pi bond. There is only one py orbital. Your atoms have every atom could have 3 p orbitals, one in the y direction, one in the x direction, and one in the z direction. So that would be like coming out and going towards you. So it only has one py orbital. These always have to be perpendicular to each other. If the nitrogen is already using its py orbital to participate in this pi bond, then the lone pair cannot also fly in a py orbital. Even if it did fly in a p orbital, it would have to be pointing in a different direction, and then it wouldn't participate in the aromaticity because it wouldn't be parallel with all of the others. And so, from either perspective that you look at it, whether you look at this from not having a Huckel's number, or whether you look at it from the perspective of the py orbital already being taken, either way, this lone pair is not able to participate in aromaticity. It is non-aromatic. It would end up being in an sp3 orbital, just pointing off in a different direction. So it's non-aromatic. But that makes it it's not especially unstable, like it would be if it were anti-aromatic, but definitely more unstable than an aromatic molecule. It would be the lone pair there would be relatively localized, and so this would be relatively unstable. In other words, it would be more likely to react, to rip an H+ off of another molecule, and this would be the stronger base. The stronger base. So the general idea here, there are a couple big points that you want to take away from this video. The first big point is that if nitrogen only has 3 bonds, it has a lone pair. That lone pair is crucial for how it's going to react. That's the first big point. Second big point. The lone pair will often accept H+, and that makes it a base. It will be a stronger base if it is localized, if it is not spread out through resonance. And the one resonance pattern you really want to remember in this context is an allylic lone pair. An allylic lone pair allows the lone pair to spread out through more than 2 parallel p orbitals over multiple atoms. It dilutes the charge and stabilizes it. And the last thing you want to remember is how to determine whether a molecule is aromatic, non-aromatic, or anti-aromatic. And we did some practice with that in this video, and if you want a more in-depth exploration of that, let me know and I'll send you some videos for that. It's in the videos for the aromatic chapter that we covered earlier in the semester.